Welcome back. Hello. Hello. All right. We keep on letting Australians into this country. The organisers keep on letting Australians speak, and we've got another one. Dr. Paris here will be teaching us some stuff about gaming, as is his wont, so let's make him feel welcome.
Awesome. Hi, everyone. It's fantastic to be here. I honestly don't remember when I submitted this talk proposal and got it accepted because it went through so much coronavirus. Oh, that's exciting. So much coronavirus time that kind of everything blurred together. So this talk has changed in concept a few times since I conceived of submitting it to this conference, but I hope it's useful to you anyway. Hi, my name is Paris. I am from Australia. I'm from Tasmania, which is the most New Zealand part of Australia, I'm told. Everyone keeps telling me that. I am the one on the left in the picture, not the one on the right in the picture. This is what Hobart looks like, where I'm from. It looks very similar to many places in New Zealand, I find. I was in Wellington yesterday, and every time I told people I was from Hobart, they're like, why did you bother coming here? It's exactly the same. So that's kind of the vibe I get from New Zealand. Ooh, that's a loud noise. I do a lot of things. I write a lot of books. I write a lot of video games. We're best known for this one, Night in the Woods, which somebody's already come to tell me they love it, which was really cool. And this talk kind of blends two of my interests, which are doing stupid things with video games and video game technology, and then attaching Python to it. And that's through the medium of a tool called Unity ML Agents, which is a specific framework that I'm going to be kind of talking about today. The technical substance of this talk is specific to this framework, but the general substance applies to lots of similar things, which I'll mention if I get time at the end. So I just want to flag that I am not a Python person, so you might see some Python scroll past in a bit, but don't judge me for how I've written it. If I don't know what I'm doing, I'm sorry. I primarily write C# and C++ for my day job, not Python. I use Python to make things happen, not super professionally. So I apologize if I do something that's not idiomatic or is slightly weird. In my defense, I am a video game developer, and video game developers do things very strangely a lot of the time, and I think we think of things in a different way than normal people. So I apologize, please bear with me. This is how a video game developer would use a microwave, for example. I'm sure you get the idea. So today we're going to talk about a little bit of the basics of machine learning. When I do talks like this at video game development conferences, I talk a lot about how machine learning works. At a Python conference, I'm hopefully assuming people maybe have a tiny bit more of an idea, but if you don't, I'm going to go through it anyway. So bear with me. And then I'm going to talk about Unity, which is the game engine we're going to look at today, which has nothing to do with Python, and ML Agents, which is the tool that we use to kind of glue Python to Unity, the game engine. And we'll show you how you can actually make a bot. So let's start with the basics of ML. So if you know machine learning, please tune out now. This is the basic stuff. Machine learning is about learning patterns from data. There's two kind of major paths through machine learning these days. There's either classification, where you give it a bucket of things and teach it how to recognize certain parts of those things, and it starts learning the patterns to label things for you. That's where you get things like this is a cat, this is a dog, this is a banana muffin, things like that. And then there's reinforcement learning, where you link actions to feedback. So instead of labeling things, you use the ability of AI to match patterns to basically reinforce certain behaviors that are infeasible to represent with a large amount of rules. Now this is particularly interesting to me as a video game developer, because in video games we build a lot of AI, which is not really actually AI, it's actually just a lot of rules. And when you have something that has lots of complex behavior, it's really hard to write enough rules to cover all the complex behavior you want. It becomes infeasible very fast. So the idea is with reinforcement learning, you can kind of define the parameters of what something should be rewarded for. Let it kind of explore the space by making random actions within the space of whatever its capabilities happen to be, and then reward it when it does something that's closer to what you want. And the more you do that repetitively, the closer you get to something that does the behavior you actually want. And the behavior also may look a bit more organic. So that's the gist of it. You describe rules for correct behavior in AI, and in heuristics, where you need something to behave in a certain way in video games often, that's too complicated. So you basically let a bot move around with random behavior, you reward it when it accidentally does the right thing, and eventually it will happen on the right thing more often than not because you've rewarded it, and eventually it'll be doing exactly what you want it to do. So hopefully that makes sense. I'm going to give a quick example now through the medium my friend and colleague, Dr. John Manning, who humiliated himself in a park in Hobart for us for this video. So I'll play the video, which has got sound, and then we'll have a little chat about what it means. It should be obvious though.
Might walk forward. Have a minty!
Thank you! Ah, brilliant.
Oh, I might take a step backwards. Give me that minty back.
Guess I'm walking forward.
Have a minty!
Hey!
So hopefully the gist of that is obvious. John is a bot in this context who is moving along a line, and when he steps forward, he doesn't know that forward is good, but he gets given a positive thing when he goes forward. He also doesn't know back is bad, but he gets a negative thing. He gets his minty taken off him when he walks backwards. New Zealanders know what minties are. Okay, good. Sorry, I've done this talk in the US, and I have to like say minty, and I'm like, sorry, candy. It's candy. What's a minty? I don't know. Americans don't know what minties are, apparently. So the goal of reinforcement learning, which is the specific kind of machine learning we're looking at today, is for an agent, a bot, I'll use those interchangeably, to learn a policy. A policy is just shorthand for correct behavior or the behavior we want, or something closest to the behavior we want. That correctly maps the different inputs it has, which are sometimes called observations or sensors, to the correct responses, which are often called actions. And when we do reinforcement learning, there are two phases. There's training, which is when we run it repeatedly, very fast usually, because computers, and teach it to do the policy that we want it to do, or get it as close to the policy we want. I say as close to because it's machine learning, right? It's not a perfect science. You're basically trying to hit a computer over the head until it does the thing you want by giving it treats. Eventually it will do it, or come very close to doing it, and then you'll declare it done. Anyone who tells you machine learning is perfect or infallible is absolutely lying their ass off to you. Once you've trained a machine learning agent, you can then use it for inference, which is just the machine learning word for use it. You've got a trained brain, a trained model, and you can basically ask it to run whatever it is you run it. So in the training phase, an agent or a bot observes some sort of information about the world that represents whatever it knows. So it might know some facts. It doesn't necessarily have perfect knowledge, so it's tempting to think of it like a human that kind of has a lot of senses. But an agent has whatever senses you give it. So it might know the location of something in perfect knowledge, or it might be able to measure its distance from walls around it, or it might know the colour of the floor it's standing on. It's kind of whatever you decide to give it. And in that world it exists, and the agent takes actions, probably randomly initially, and those actions are whatever you let it do. So let's say you've got a thing that exists in a world that can move, you can make it move left and right, back and forth. That might be all its actions. The actions are whatever you've given it. And then once it's taken an action, it's rewarded based on whether that action met some conditions that you defined. And eventually, the more rewards it gets, the more it learns to do the right thing every time. So that's the gist of ML. I'll hope it'll become more apparent as we go into Unity. So ML agents, still not Python. I'm not a Python person, so please forgive me. There will be Python eventually, I promise. ML agents is the Unity framework that plugs Python into the Unity game engine. So the Unity game engine is a big, popular game engine used by maybe 60% of the games industry. It's not without controversy. Don't Google Unity right now. The CEO said some stupid stuff recently. The developers are lovely, though. It went public. You get the idea. In ML agents, the agent perceives its environment, which is a 3D world or a 2D world that kind of has enough of the real world simulated. It's got physics, it's got the ability to detect when it's touching something, it can see things if you want it to. It runs that observation reward cycle within Unity. So within Unity, there is an agent. The agent is in an environment which is a visual scene that you can look at. It has certain actions it can do, which are realistically probably movements. Let's face it, this is a game engine. It excels at simulating physical things. It collects observations about the environment, which are just numbers that you are feeding into it, that you have chosen to feed into it. And it receives rewards, which are again just numbers. You can't give digital minties in this case, it's just a number. A positive number is good, a negative number is bad. And it does whatever it needs to do. So looking back at John, the agent is John, the environment is a park. The actions are step forward, go backwards, maybe you can turn. We didn't see it in the video, but there's another video in the secret extras. He knows his own position on some sort of linear scale, and he knows Tim, the person handing in the minties position. And he gets a reward when he moves forward, and he gets candy taken away when he moves backwards. That's very it. That's it. So Unity has a concept of a game object, which is made a type of agent. It has a scene, which your environment is, and so on and so on. So let's actually take a look at Unity now. This is definitely not Python, much. Now I'm going to do something very foolish. I decided to replace my pre-recorded demos with a live demo. So please forgive me if this goes wrong. I'm going to step out of here and turn off mirroring. Turn on mirroring. That's the one. Okay, this is Unity. It looks like every other piece of professional 3D software, and that for some reason they decided to make it dark. Don't really know why. It's a 3D environment, so it's pretty much bog standard in 3D environment. You can create things in this environment. There's a cube I've created, right? You can create I named it F for some reason. You can create, spheres, and you can move them around. Okay, I'm sure everyone's seen something like this. It looks a bit like Blender, if you're familiar with Blender or any of the 3D modeling packages, but it's got a lot of other logic you can do. So Unity lets you assemble scenes in this 3D world and give them physical behaviors, physics, weights, things like that, and it will happily simulate those things for you. It's very simple, and it's kind of a component-based system, so each of these objects can then have a script attached to it by clicking here. So I can then put all kinds of objects on it, and I can just go new script, then I make a script, it attaches the script to it, and then it responds to the world through that script. So everything's kind of decoupled in a fairly unique way that's very common in game development. That's a really simple Unity scene. I'm going to show you one that actually has an agent in it, which is this one. So in this scene, I have made a floor. This is the floor here. It's just a plane. So it's got a flat mesh that's just a plane on it. And on that floor, I've placed a cube. The cube is just a cube, nothing special about it. And by placed, I mean I have turned on the physics engine and placed it as precisely as I can above the floor. When I run the simulation, the physics engine will make sure it falls and hits the floor, and then it will stay there. That's it. I've also placed a ball in here, which is just a sphere. It's just a nice sphere mesh that I've dropped on this floor. And to this ball, I've given a rigid body. This means it can perceive when it is hitting other things. So there's a difference between being in the physics engine and being able to hit other things, which is what the cube has, and being in the physics engine and being able to hit other things and do something when they hit something, which is what the ball has. So the ball has the ability to basically run a callback when it hits something. To that ball, I've also made a script. This script is an agent script. It's C#, it's not Python. So it's called ball agent. I'm just going to quickly show you that because it's kind of brings the concepts together. This ball agent script, when it starts, so when the simulation is run, it resets its position back on the floor. So if it falls off the world, it puts it back on the floor. And it randomly places the target cube, which is the cube that exists in the world. So it randomly moves it somewhere else on the floor. Here's the collect observations method, which we override. This is actually our learning about the world. So the information this agent, this ball agent, has about the world is the position of the cube. It knows the exact position of the cube it's trying to find, and it knows its own position. Okay? It also knows its own velocity on both axes. Those are its entire knowledge about the world. It knows nothing else. That's its entire knowledge. When it is told to move, it can roll in all directions, basically. That's all this bit does. If it's very close to the target, which is the cube, it gets rewarded. Okay, we give it a 1.0 float. That's it. If it fell off the platform, we end the episode and start again, which basically calls that reset earlier we saw. This method here is called heuristic. It just allows us to drive it with the keyboard. A really good thing to remember when you're building virtual environments in a game engine to train agents is that if you can't drive the agent around within it, if it's a moving agent, the AI will probably struggle as well. So I'm going to go back into Unity. That's the wrong Unity. As a game developer, I always have like 100 Unities running, so it's really just very stressful. I'm going to run this now. Just going to delete that. I'm going to run this now, and you can watch me badly drive this ball around with the keys on the keyboard. So you can see I am rolling the ball with the WASDF keys. When I drop off the edge, it resets. Whee! Fell off, but if I manage to hit the thing, it resets the position of the thing. Oh, I fell off again. Get the idea. Okay, so this is our agent. We want to teach this agent to track that square. This is where the Python comes in. So ML agents lets you define a whole bunch of hyperparameters, which are basically machine learning training parameters that tell the machine learning subsystem, which in this case is PyTorch, how to work. I'm not going to go into this today because it's basically more complicated than anything else I'm talking about, and we would get bogged down all day. But you can specify which algorithm you want. In this case, we're using something called PPO. Has anyone heard of PPO? Hopefully, yeah. It's called proximal policy optimization. It's kind of one of those things that a lot of luminaries in the AI world wave around as like the one generic machine learning algorithm that's useful for everything. It's not really that. But what it is it's suitably generic to do a lot of things with. So it's a machine learning algorithm that performs gradient descent on whatever you give it and converges on a sensible policy in many situations related to this kind of machine learning. It's not perfect in all situations, and there's a few other machine learning algorithms you might want to explore, like MAPOCA or things like that. But this one is good in enough situations that it's a really good starting point when you're doing this kind of visual machine learning. All the other things are basically how long it trains for, how it learns, whether it has memories of previous training cycles, things like that. So we basically make a YAML file because, you know, what project doesn't start with a YAML file? And then we run this mlagents-learn Python script, which comes with this mlagents package. We tell it about the YAML file and we give it a run ID. I'm giving it Kiwi 2 because I've already trained this a few times, so we just want the run IDs to be different. You can run it multiple times with the same ID to give it more information, so you can stop and start the learning process. Or you can change it slightly between learning process to basically create new paths through the model. So I'm going to run that. My computer's going to freak out for a moment because I have too many Pythons and too many Unities. So we'll just let that freak out. But once that's finished running, we'll get a nice ASCII version of the Unity logo, which is very exciting. And it will say it's listening on a port. So then we go back to Unity, and we push play. Unity hopefully doesn't crash. Oh, it crashed. Interesting. Oh, ball, right, okay. That's my bad. Let's balance it, not ball. Kiwi 3. Sorry, I was pointing to the wrong YAML file. Okay. Okay, so now what Unity is doing is basically sending completely random actions to the ball agent within the spectrum of actions the ball agent can take, which is just rolling left, right, back, forward. And sometimes that ball is accidentally hitting the box. Every time the ball accidentally hits the box, Unity says that's really good. Well, PyTorch says that's really good. Do that more. So slowly, the longer we run this will eventually converge on hitting the box every time. And because this is so simple, this won't actually take very long. It'll take about 15 minutes on this, which is the cheapest MacBook Air Apple currently sells. But you know, Apple Silicon's pretty grunty, but even then, like, this kind of agent can train very quickly. If you have like an NVIDIA graphics card or some sort of bank of TPUs somewhere, you can do this in seconds, which is great fun. If you have use Google Colab, you can actually run Colab to do this, which is quite effective. And you can let Colab talk to your local copy of Unity, which is nice. That's what I do usually, because I'm lazy. And Colab is way too useful for this kind of thing. But basically, this will run for a while, and eventually it will finish. It will finish when it runs, so if we think back to this YAML file I made, there is a max steps here. So when it hits that many steps, it will stop. You can just restart it with more steps if you want to increase the amount of information, but that will take a little while. You see here we've hit 10,000 steps already, and you'll see the mean standard of the reward is 0.5, which is not very good, but it will slowly get better. If you're familiar with TensorBoard, which is useful for monitoring machine learning training, you can run that now as well and watch the log directory to see its sort of number go up, hopefully. Eventually it will train. So I'm going to stop that now because that will take the rest of the presentation if I let it run and show you one I already built. But you'll see here when I stopped it, it wrote out an ON and X file, which is, I guess it's converged on the industry standard for a neural net file. That's just a bunch of numbers that tell us how to process the numbers that go through it. And Unity understands what an ON and X file is, and if you drop it in Unity, it will represent it as a little neural net. You just put it in the project directory, and then we can drag this ball into this slot over here, where it needs a model, which means now we do not need me driving it around, and we do not need the Python connection under the hood anymore, and it will do its best to consistently roll into the thing. That's not with me doing anything, right? So we've trained a very useless ball, but hopefully you can see the potential here. So now I'm going to show you a couple more advanced things before we wrap up. So that's our agent, it's doing something. Let's take a look at a more interesting one. This is a box. This box is attempting to learn to balance the ball on its head. I've only trained it for 5 minutes because I was doing it over breakfast at the hotel this morning. But the interesting thing about this box is it's learned to do this not with any sort of numerical observations that I've given it, but with a camera. So because Unity is a game engine, we are seeing this scene through a camera which is positioned in the scene. So the camera that you are seeing the world through is this thing here. So you can see like the frustum of the camera, which are those like pale white lines, which is giving you the perspective that we were watching. But there's a second camera in this scene, which is here, pointing down, and you can see it down here. An 84 by 84 pixel grayscale version of that camera is being sent into PyTorch this time. And that's the only observation that has. And it's been told if the ball falls off your head, you get a large penalty. Otherwise, if the ball's on your head, you get a very small positive reward every tick. And from that, and then from that alone, it's learning how to keep it on its head, which I think is really cool. So I'm just going to show you one more thing, and then I'll show you a quick snippet of Python, because this is a Python conference. But I promise you there's lots of Python going on under here. This is a way more complicated one. This is a worm that's learned to slither. Now, I kind of made it look like the Kiwi PyCon colors because it's kind of Python-esque, but it's actually a worm. I'm sorry, it's not a Python. This is not animated. This is a bunch of segments that have moving joints, and its actions are rotating those joints. And its reward is moving with the head pointed at the green cube and eventually touching the green cube. So it's geometrically rewarded based on previous sessions when it points at the cube with its head, slithers in a worm-like fashion towards the cube, and eventually touches the cube. And when it hits the cube is, it's much like life. When you reach the goal changes. But this little worm has learned to do this. This is about 3 hours of training on a 1080 Ti. It's not actually that much time realistically, and it's a pretty old GPU. But this is the kind of behavior you can get if you're willing to put a bit of time into it. So I'm just going to quickly show you a little segment of Python now. All of this can be fully controlled with Python. So what I've got here is I've got a Jupyter notebook running in the same environment as the rest of the Python stuff. And we can actually go through and grab environments out of of course it's erroring now. I'll show you a different one. We can go through and grab Python environments out of a pre-built environment, or we can just build something out of Unity as a binary and then run it ourselves. And what this does is this lets us grab, oh my gosh, ports, macOS, what are you doing? Okay, so this has just launched this binary down here, which is food collector apparently. That's not the one I wanted to run, balancer. Okay, we need to go 5001. There we go. So I've run a Unity program. I'm going to go back in here. Python has launched it for me. I'm going to go, what kind of observations do you have? I have a visual observation. So this is that one with the balancing. Yeah. This is the one with the balancing cube that had a ball on its head. It knows that it has one visual observation. It knows it has two continuous actions, so it can rotate it sideways. That's all it can do. It knows it has no discrete actions. Then we're going to invoke matplotlib. And the really magical thing is you can basically grab the visual observations out from in Python. So you can treat ML agents, which is the Unity framework, as basically an API to control Unity with for whatever nefarious purposes you have. So if you want to build something that has a 3D world, you can then control it fully from Python using this, which I think is really cool. So you can actually ignore the ML component entirely if you want, just to have an API into Unity from Python. But also you can replace the training pipeline. So this is a full-on, it's going to error again, but this is a full-on custom training pipeline where we do Q-learning, which is a completely different type of machine learning that PyTorch and Unity do not support together, where there's a whole custom algorithm written here in Python that is controlling a Unity environment. So that's pretty much everything I wanted to talk about today. I hope that made sense to you. I have time for questions, I think. I have 6 minutes maybe, if I've counted correctly. Yes. So does anyone have a question, or do they just want to shout at me or tell me there was not enough Python in here? That would be fun too. But thank you for listening. Yeah?
Yeah, I have a question.
Oh, Katie's got a mic.
Thanks for the talk. Interestingly enough, I lecture and I use ML agents for my classes, and I find it great. You mentioned some controversy around Unity.
Yes.
And obviously being in a university,
Yes.
there's a lot of ethical discussion in that. So I'm just wondering if you might have any ideas what I might replace ML agents with.
Yeah.
Because I see that you did have Godot, for example.
Oh yeah, we use everything because we're game developers, so we're very platform agnostic. No, I have no idea. Nobody has got as mature an ML framework as Unity right now. I do know Unreal is working on one. I do know there's some community efforts in Godot. I do know if you are particularly tenacious, you can kind of bolt ML agents into Godot using its C# version, because Godot has a C# version and ML agents really understands that. But no, there's nothing as mature as this. There's like the OpenAI gyms, which do the same thing, but without the game engine component. They're all kind of a custom 3D world. So no, I would not say there's nothing as good as this. And I say unfortunately because Unity is fantastic technology with just this weird corporate thing attached to it, which is a big shame. We wrote a book on it, and I'm not really here to sell you the book. The book is more for game developers to learn about this stuff more than it is for Python developers. But I don't trust Unity, which is my concern. They throw this fantastic technology out and then they just ignore it. Yeah, sorry, I haven't got a better answer.
Thanks for the talk. Just a question. I didn't quite catch how you managed to get PyTorch integrating with Unity, and is that a built-in feature?
So it's a Python package called ML Agents, all lowercase, all one word. So if you just pip install ML Agents, you get everything you need to do this. It's fantastic.
Thank you.
It is not in Anaconda, unfortunately. I kind of wish it was in Anaconda's repository, but it's in pip.
A quick question. If you train an agent, how costly is it to include it in a game?
So Unity has its own built-in inference engine, which they call Barracuda, which does not rely on PyTorch. So if you're shipping a Unity product, you do not need to ship any Python components, which is probably a positive and a negative depending on what you're doing.
Do you know what the impact on performance for your game would be, or compared to hard coding behavior, for instance?
Oh, look, once it's in the game, the performance is very good. If you're running it on a modern Android device, a modern iPhone, or a modern Mac, or a computer, or any PC with a GPU, your performance will be perfect. But if you do not have a GPU, you might have some problems.
Any other questions?
Nope.
All right, let's give Dr. Paris another round of thingy.